How does the body know when it's time to grow and when it's time to shrink? Let's talk about it. I'll see you inside. Today is really going to be a culmination of a lot of research, and I really hope you enjoy it. We're going to take a look at how the body is actually able to sense the amount of nutrients inside the body. And with this, it can really tell all the cells inside of our body whether or not it's time to grow or it's time to shrink, whether or not they should be taking nutrients from the bloodstream or whether or not they need to rely on the nutrients they already have in storage. Additionally, the body actually has the ability to really tell our entire physiology what fuel source it should be relying on. For example, if we're low on a specific fuel source, we will actively conserve this fuel source in order to provide it to all of the tissues and cells that actually need it. Like when we're fasting, the muscles will actually stop taking up glucose and the brain will actually take up almost all of the glucose. The muscles become slightly resistant to glucose, and the brain continues to uptake the same amount of glucose. And the liver is actually taking the glucose it has inside of its cells and pushing it into the bloodstream so the brain has a fuel source. And you see, the body has the ability to regulate all of these cells through different hormones so that each different organ and tissue is doing its job properly. With that being said, today I really want to highlight 6 different nutrient sensors. So the first thing I want to say is that the body has 3 different macronutrients: protein, fat, and carbohydrate. And we have hormones that really signal to the body how much of these we have around. And there are different hormones for when we have a lot of protein versus when we don't have a lot of protein. And the same is true for fat and glucose. Let's start at everyone's favorite macronutrient, protein. The 2 specific molecules I want to talk about are not actually hormones. These are actually proteins that are found inside of almost every cell. And these molecules sense the abundance of proteins in the environment and can cause the cell to either go through what's called protein synthesis, which is the building up of muscle, or through a process called autophagy. And autophagy is simply just this recycling system that occurs inside of the cell. You see, when we're making proteins, we produce so many proteins that not all of them are going to be perfect. So sometimes there are just proteins that are kind of floating around, not really functioning the way we'd like them to. And when we have sufficient protein coming in, we don't really have to worry about it because we simply make new proteins that take their place. But when we're in a state where the cell is actually low on energy and amino acids, we'll actually begin this recycling process where we simply break down proteins that we've already made into their individual parts. And then we use these parts to actually reformulate new, healthier proteins. And before we dive too deep into this, there are some prerequisites that are important to know. The big thing is that all proteins are made out of what are called amino acids. Think about a chicken breast just being a big clump of amino acids, and some water and other vitamins. You can think of proteins as being the house and amino acids as being the bricks. And we have 23 different amino acids that we'll use to synthesize proteins inside of our body. And different amino acids can actually do different things. For the most part, amino acids are just used for protein synthesis. However, there are a few amino acids that can actually serve as signaling molecules. And this has kind of sparked an interest in trying to supplement with specific amino acids. However, you'll be able to get in all of the amino acids you need simply if you eat the right foods. Luckily, the amino acids inside of animals are the exact same as the amino acids in humans. And what's even better is that they come in the ratios that best promote protein synthesis in our bodies. And I think this is where the dietary concept of eating an animal nose to tail really shines. So most of the structures inside of our body are actually going to be made out of amino acids. And the thing that differentiates something like our muscle from our skin is just the composition of amino acids. And really, animals have the exact same composition of these amino acids in their muscle or their skin. And this is where the concept of eating animals nose to tail really shines. Eating muscle meat will provide you a great amino acid ratio for protein synthesis for your muscle tissue. But it may not provide amino acids in the best ratio to support things like collagen tissue growth or maybe organ health. But something like organ meat has amino acids in a ratio that's more favorable for supporting the health of our organs. And the same goes for collagen tissue. So although most people don't want to hear this, eating organ meats and the collagen-rich portions of meat really gives us all the amino acids we need in just about the perfect ratios, which means trying to diversify your protein intake just a little bit. So really just eating mainly muscle meat, and then maybe once a day or once every other day trying to get in some sort of organ meat and collagen-rich proteins such as gelatin and maybe the bones of small fish like sardines. But this is entirely up to you. I don't really remember why I got down that path, but what I really wanted to talk about was how the body responds when there is and is not enough protein. So inside the cell, we have two different proteins. One is called mTOR and one is called AMPK. And these two proteins really interplay with one another beautifully. mTOR will actually inhibit AMPK, but AMPK will also inhibit mTOR. And really, what determines who is inhibiting who is the energy state of a cell, specifically in terms of protein. So some of the amino acids that we eat, specifically the most notable would be leucine, actually has the ability to increase the activity of mTOR. Meaning the more leucine, which again is just an amino acid, the more activity of mTOR we have. And now this does cap off at about 5 grams of leucine because it seems to maximally stimulate mTOR because we only have so many of these proteins inside of our body. And you can get this 5 grams of leucine from something like 20 to 25 grams of chicken, beef, and fish. But what mTOR is going to do is it's actually going to bind to this AMPK molecule and completely turn it off. So the way that mTOR works is through what's called phosphorylation. So inside the cell, we typically will have a lot of just free-floating phosphate molecules. And these molecules are actually used to turn off or turn on specific enzymes and proteins at different times. And when mTOR gets activated, it will take these phosphate molecules and attach it to other proteins inside the cell, once again turning them on or off. And some of these proteins include actually inhibitory proteins that may bind to a specific enzyme and not allow it to function. And other times it may add a phosphate to an enzyme directly and the enzyme will upregulate its function. And one of the biggest things that mTOR will do is actually put a phosphate on what are called transcription factors. And these are little proteins that sit kind of dormant inside of the cell. But when we put a phosphate on them, they'll actually go directly into the DNA and start encoding for new proteins and organelles. And this is actually how most hormones and neurotransmitters function. And in the case of mTOR, almost all of the proteins that will be turned on or off lead to the upregulation of the process called protein synthesis, which is increasing the amount of proteins we have inside of the cell. For example, some of the things that mTOR will do is actually increase the production of amino acid channels. And these channels will bind to the membrane and allow more amino acids into the cell. Therefore, we can make more proteins. And in doing so, we won't rely on the proteins that are already inside of the cell. And then mTOR will cause the production of specific enzymes that actually promote the entire protein synthesis process itself. So the best way to think about mTOR is that when we have an abundance of amino acids inside of the bloodstream, some of them can get into the cell and bind to mTOR and turn on mTOR. And then this little protein inside of the cell will cause the production of a whole bunch more proteins. And it will inhibit AMPK from trying to break down the proteins we've already created. And I'll actually talk about how this could be both good or bad in a moment, but first let's talk about AMPK. So AMPK is another protein that probably sits right next to mTOR inside the cell. And simply when we don't have a lot of amino acids in the bloodstream, mTOR won't be activated and it won't be inhibiting this AMPK molecule. And the other thing that will actually stimulate this AMPK molecule is an imbalance between energy use and energy availability. So all of the energy inside of a cell, for the most part, is derived from a single molecule called ATP. And this is short for adenosine triphosphate, and it's simply an adenosine molecule with 3 phosphates attached. And the way that we actually get energy is simply by breaking the bond between the second and third phosphate. This releases energy that we actually use to stimulate things like muscle contractions, thoughts, and just about everything else. So then we're left with a phosphate and an ADP, or adenosine diphosphate, which is just an adenosine molecule with two phosphates attached. And there's a lot of different ways we can recreate ATP, but one of them is actually taking two adenosine diphosphates and transferring one of the phosphates from one of the ADPs onto the other one. So then we create an ATP, adenosine triphosphate, and an AMP, which is adenosine monophosphate, or 1-phosphate. Think about me taking my left arm and giving it to you. You now have 3 arms and I only have 1. And the ATP can then again go be used for energy, but this AMP actually has a signaling role. So AMP can actually bind to AMPK and activate it in the same way that amino acids will activate mTOR. And beautifully, AMPK, one of the first things that it will do is quickly inhibit mTOR. So it stops mTOR from trying to make more proteins, which kind of makes sense because at the moment the cell is kind of in a low energy state, and this will typically occur upon fasting and exercise, or even better, fasted exercise. And AMPK really does the exact same thing as mTOR, except the proteins that it upregulates are actually important for a process called autophagy. And this really is the recycling process where we switch from using endogenous amino acids coming from the bloodstream, and we make a switch to using the amino acids we already have stored inside of the cells, but they're just contained in preformed proteins. And luckily, the body is pretty smart, and it will actually choose the misfolded and damaged proteins to recycle and replace. So by inhibiting mTOR, we'll stop the production of more proteins, and if needed, we'll go through this autophagy process to recycle amino acids to create necessary proteins. Another thing that AMPK will do is actually activate the enzymes involved in fatty acid catabolism, which is simply just the breaking down of fat. And it's also smart enough to inhibit the enzyme responsible for increasing triglyceride storage. So the net result is we stop storing fat and we begin to utilize it for energy, creating more ATP, which is the signal that we're responding to in the first place. It will also cause what's called the translocation of glucose receptors. And these are simply just receptors that are inside the cell. And this translocation process simply means they go from inside the cell into the membrane of the cell, where they can now allow glucose to freely enter the cell. And once again, this little protein is pretty smart, so it's actually going to inhibit the enzymes that are involved in glycogen synthesis. Because when glucose enters a cell, it can either be used for fuel, or it can be turned into glycogen, or it can be released from the cell and turned into fat. And in a state of decreased ATP, the main focus is going to be making more energy now and not saving energy for later. So we increase glucose uptake and we inhibit the storage of glucose into glycogen, meaning we will immediately utilize this glucose for ATP. With that being said, before we move on to the other macronutrients, I just want to mention that none of this is actually occurring in isolation. All of the proteins and hormones and neurotransmitters that I mentioned today are just a very select few of proteins inside of our body that do seem to be the major regulators of certain processes. And in the case of regulating and sensing how much protein we have available, the two ones that we focused on were mTOR and AMPK. And before I move on, I'll just mention how these two molecules are implicated in things like aging and disease. So oftentimes fasting and caloric deficits, which would increase the activity of AMPK, are promoted to increase longevity. And this is because the process of autophagy is actually going to remove some damaged or misfolded proteins that we simply don't want aggregating inside of our cells. Additionally, it may have the ability to actually stop cancers from growing and replicating. But this is likely less due to AMPK activity and more due to the lack of mTOR. Because without mTOR, we're not going to grow and divide, which means we don't facilitate the expansion of cancerous cells. And while it may sound scary, there's a lot of cells inside of our body that accumulate every single day that could technically become cancerous cells. And the only way cancer actually develops is if these cells begin to replicate and they develop a mutation where their replication does not get inhibited. So trying to limit mTOR would reduce their ability to replicate, and increasing AMPK and specifically autophagy would increase our ability to actually scavenge these cells and these damaged proteins and maybe recycle them. With that being said, without any mTOR, we're not going to grow muscle whatsoever. And a lot of times in a state of high AMPK where we're constantly breaking down, not only will we lose muscle, but we may actually reduce our immune system. So you really want to find a good balance between having enough mTOR to promote the positive growth like muscle and immune function, and don't forget cognitive function, but also inhibiting mTOR every once in a while simply so we can increase the activity of AMPK and get all the benefits of this recycling process that this protein is involved in. And it will also aid in the fat loss process, as we mentioned. But remember that AMPK is also upregulated during exercise. Therefore, the process of exercising will increase AMPK, and then the process of eating protein afterwards will increase mTOR and allow us to repair and grow stronger from this exercise. So we really can get the best of both worlds if we limit mTOR simply by exercising. And then when we eat protein, we'll send the signal that there's protein available. So we'll increase the activity of mTOR, which will benefit us by increasing protein synthesis. Alright, so the next macronutrient that we'll talk about are carbohydrates. And you may know the hormones that really regulate our carbohydrates and can signal carbohydrate availability around the body. These include insulin and glucagon. So these are two hormones that are actually produced inside of the pancreas, and they really respond to the blood glucose levels. And now you may have heard me mention many times how the way that glucose gets into the muscle cell is through a GLUT4 receptor. And there are different things that actually cause this receptor to translocate into the membrane and allow glucose in. One of them being exercise and the other being insulin. But the beta cells in our pancreas, which is actually where insulin is produced, also needs glucose in order to actually stimulate the production of insulin. But since insulin is what we're trying to produce, we won't have the insulin around to stimulate this glucose uptake inside of the pancreas. And there really is no way to exercise the pancreas cells, so how in the world is this glucose going to get inside of the cells? Well, the pancreas actually has a different type of glucose transporter, and it's called a GLUT2 transporter. And they don't actually use insulin to stimulate their translocation from inside the cell to the membrane. So these transporters are simply just always on the membrane, and they're always allowing glucose into the cell. And inside the beta cell, once again, where insulin is stored, insulin is sitting in a little vesicle. And upon the entrance of a lot of glucose, the cell will begin to make more ATP. And we actually have little channels on our cell called potassium channels that this ATP can bind to. And when it binds to these channels, the cell stops letting these potassium ions out of the cell. And what's important about potassium is that potassium has a positive charge. And when this potassium builds up inside the cell, the voltage of the cell will increase. So now we've got lots of potassium inside the beta cell because there's lots of glucose going in. Well, the one last protein that we'll have to remember is what's called a voltage-gated calcium channel. And in order for us to actually release this insulin into the bloodstream, we actually need calcium to allow the vesicle to bind to the membrane and release the insulin. And remember, this potassium increased the voltage. And when the voltage surpasses a specific point, these calcium channels will open, and the whole process of this vesicle fusing to the membrane and releasing the insulin will occur. And I only explain this just in case you were really wondering, but all that really matters is that the more glucose that is being uptaken into the cell, the more ATP we will produce, therefore the more insulin we'll produce. And now insulin has receptors all over the body, in the brain, the muscle, the adipose tissue, the heart, the kidney, really everywhere. And at the muscle, what it does is it will allow GLUT4 receptors that we discussed to embed themselves into the membrane and allow more glucose into the cell. And the muscle is really only going to do this upon insulin stimulation or exercise. But in terms of insulin stimulation, it's because insulin is a signal that there's exogenous glucose, which means there's enough glucose available in the bloodstream for the brain and all the other organs, and enough for the muscle to uptake glucose. Really, the muscle is the last organ that will actually uptake glucose because there are certain organs, like the brain, that is going to derive almost all of its energy from glucose. And if you really want to learn more about this, episode 23 and episode 41 go much more in depth on this topic. But it's important to remember that insulin goes up when we ingest carbohydrates, and this is the body's way of sensing that there are external carbohydrates coming in. And when there's enough circulating insulin that insulin binds to its receptor on the muscle, we use these GLUT4 receptors to actually intake more glucose. And I didn't even mention that insulin doesn't actually go inside of the cell. Insulin just binds to the receptor, and there are little proteins inside the cell that get activated when insulin binds to the receptor. And then all this phosphorylation starts to happen, and one of the things that occurs is these GLUT4 receptors. Other things that get phosphorylated, once again, are things like transcription factors that bind to the DNA and encode for specific proteins. What's very interesting is that the mTOR protein we talked about earlier is one of the proteins that insulin can stimulate. And this is specifically going to be in the muscle tissue. So insulin, just like protein, could actually increase protein synthesis by activating the molecule that's really governing the entire cascade. It also increases what's called glycogenolysis, and this is simply using that glucose that we are uptaking and creating glycogen. So really the opposite of what that AMPK molecule is doing. Because once again, the AMPK is a signal that we don't have much energy, but insulin is a signaling molecule that we have an abundance of energy, specifically in the form of carbohydrate. Insulin can also bind to the liver and cause the liver to upregulate the production of enzymes involved in glycogen synthesis. So we store more of the circulating glucose inside of the liver for energy later. And unfortunately, it does also stimulate the fat cells, and it will allow glucose into the fat cell, which is actually used to create stored fat, which are triglycerides. Glucose is converted into glycerol, and glycerol is what 3 fatty acids are attached to form a triglyceride. And this is how fats are stored inside the fat cell, and the more triglycerides we have, the larger the fat cell. And one of the other effects of insulin is actually decreasing the enzymes that actually can liberate these triglycerides and allow fat out of the cell. And it will upregulate the production of enzymes that are involved in forming these triglycerides. So long story short, at the fat cell, it allows for fat cell expansion and stops us from actually taking any nutrients out of the fat cell. And at the liver, it increases stored glucose. And at the fat cell, it increases glucose storage, use, and protein synthesis. And it has similar effects in other tissues like the brain, where it really promotes energy uptake and energy usage. And one of the last things it does is actually inhibits the production of the next hormone we will talk about, which is glucagon. And glucagon really is the exact opposite of insulin. So right next to the beta cells in the pancreas, we have the alpha cells, and these cells don't produce insulin, but they actually produce glucagon. And the way that the body actually regulates the production of glucagon and insulin is that these glucagon-producing cells have insulin receptors on their membrane. And when insulin binds to the receptor, it actually inhibits the production of glucagon. And I've spoken about this before in my episode titled The Diabetic Paradox. But when we begin to develop insulin resistance, where we are producing insulin in response to elevated glucose, however, the insulin receptor is not functioning properly. So the signal isn't sent to the glucagon-producing cells, so we will continue to produce glucagon. And as I will discuss in a moment, we actually only want glucagon elevated when we have low blood glucose, because glucagon's role is to increase the amount of glucose we have in our bloodstream by releasing glucose we have in storage. But insulin is responding to glucose that we're eating. So both of these actually work together to radically increase our blood glucose to levels that are actually harmful. And this is something that typically develops after eating a lot of carbohydrates for a long period of time, which causes us to have to overproduce insulin for long periods of time, and the way the body adapts is simply by downregulating the function of the insulin receptor. So even though there's a bunch of glucose floating around, the body doesn't actually start any of those processes I discussed earlier, because it is actually the insulin receptor that causes all of them to occur. But in a healthy human being, insulin can bind to the alpha cells that produce glucagon and stop this glucagon release when we have insulin present. With that being said, let's talk about glucagon and how it both responds and regulates our blood glucose levels. So glucagon levels are increased when we are not ingesting glucose, and they increase in response to a falling blood glucose level. And really the only way we can have this occur is if we're not eating any, which means we don't have any exogenous glucose coming in, meaning we need to free up all of the glucose that we have stored and actually create new glucose. And once again, why would we actually need glucose? This is because there are certain cells inside of our body that simply need glucose. Probably the most important ones are going to be the brain. With that being said, once we go beyond a very low intensity exercise, and we get into activities like higher rep weight training or longer jogs such as a 5K or a mile, we're actually going to be required to use a lot of glucose because there are certain intensities that we can't use fat for fuel. And I think the best refresher on this subject would be episode 44, called The Physiology of Endurance Adaptations. So glucagon's role is to keep our blood glucose normal, and it senses the amount of carbohydrates we are eating, and if we are not eating enough, then glucagon will increase. So in a healthy person, insulin and glucagon work in tandem to sense the amount of carbohydrates that we have available, and sense the amount of carbohydrates that we are eating. Before I keep rambling, let's talk about glucagon. So glucagon is produced in the alpha cells when the cells are low on glucose. On the alpha cells, there are what are called GLUT1 receptors, which also let glucose freely into the cell without the need of insulin. And these cells also function in an ATP-dependent manner. However, they're a little bit backwards. So when we have low blood glucose, less glucose will be going into the alpha cells, and there will be less ATP. And this low ATP will actually cause what are called ATP-sensitive potassium channels to close, as these channels require ATP in order to open. When they're open, they're letting potassium out, and when they close, the potassium begins to accumulate inside the cell. Very similar to the way that insulin functions, except in these cells, they respond to increasing ATP, and the ATP actually causes these channels to close. In the case of the alpha cell, ATP causes these channels to open and allow the potassium out, meaning that low ATP will cause these channels to stay closed, meaning there will be an accumulation of potassium. And then the same process occurs where the voltage increases and allows calcium inside the cell. And once again, calcium can allow the vesicles containing glucagon to fuse to the membrane and release the glucagon into circulation. And just like insulin, glucagon binds to its receptor, which causes a very similar cascade of phosphorylation events, leading to the transcription of different proteins inside of different cells. And it will also inhibit the activity of other enzymes. So in the liver, it will actually inhibit enzymes required for turning glucose into glycogen. And it will upregulate the enzymes that actually take the stored glycogen in the liver and turn it into glucose. So the net result is that the stored glucose molecules that come in the form of glycogen that are stored inside the liver are broken down and released into the bloodstream, which will raise our blood glucose levels. It will also inhibit some of the enzymes that are responsible for breaking down glucose into energy, and stimulate some of the enzymes that are required for making glucose. So the liver will stop using glucose as energy and rely more on fatty acids, and any excess energy that there is available, it will turn into glucose to secrete into the bloodstream. It also increases enzymes responsible for what is called gluconeogenesis. And this is the conversion of non-glucose molecules into glucose. The most predominant molecules used are going to be amino acids, which remembered are the building blocks of protein, glycerol, which is actually a part of stored body fat, and lactate, which is a very interesting subject that I hope to do a podcast on because it absolutely is not a harmful byproduct of exercise. And it's actually used as an energy source for most of the tissues in our body, specifically the heart and the brain. And we produce a lot of lactate even at rest. And when some of this lactate is in the bloodstream, the liver can actually uptake the lactate and turn it back into glucose. But where are we going to get this glycerol and these amino acids? Well, glucagon will actually go to our adipose tissue and increase the functioning of the enzymes that will take the stored triglycerides and release free fatty acids and glycerol into the bloodstream. Therefore, we'll begin to use less glucose and more fatty acids for energy because they are now available inside of the bloodstream. And the glycerol is used once again for gluconeogenesis. Because if you remember the insulin story, the way that glycerol was actually formed inside of the fat cell was simply by taking in glucose and transforming it into a molecule of glycerol. And in the liver, we just reverse this process. Glucagon will also inhibit those GLUT4 receptors on the fat cell, so no glucose is going to enter the fat cell. But this is mostly mediated by the lack of insulin. With that being said, glucagon really doesn't do much to actually break down muscle, meaning that it likely won't go to the muscle tissue and start breaking down the muscle into individual amino acids to use for gluconeogenesis. However, when we have simply used up all of this stored glucose that we have, our blood glucose will begin to lower. And if there is no more stored glucose, then we will turn to amino acids to upregulate gluconeogenesis. But the first thing that will happen is actually our blood glucose will lower and the brain will actually fall short on glucose for a period of time. And this is actually going to increase the production of specific hormones in the brain. The most notable one being cortisol that will actually promote the breakdown of amino acids. Simply, cortisol is a much more intense version of glucagon. But glucagon is really focused on stored glycogen and upregulating the burning of body fat so we can preferentially save glucose for the brain and tissues that need it. And once again, it's going to increase all of the enzymes that we need for stopping the storage of glucose, increasing the production of glucose, and increasing the utilization of fat, and to a very minor extent, the actual use of amino acids for energy. And there are a few other hormones and different molecules inside of our body that really regulate both glucagon and insulin production and signaling. And I'm going to talk about two of them in much more depth in a moment, and these are neuropeptide Y and leptin. Leptin is going to increase the sensitivity of insulin, but neuropeptide Y can actually inhibit insulin signaling. And glucagon has a regulatory role of inhibiting insulin, and insulin has a regulatory role of inhibiting glucagon. And some other things that will downregulate insulin signaling are epinephrine or adrenaline, growth hormone, cortisol, and actually some inflammatory molecules called inflammatory cytokines. And it actually appears that high amino acids can also inhibit glucagon. And once again, so can high glucose. So what we've covered so far is that mTOR and AMPK are really the nutrient sensors for protein, and insulin and glucagon are the nutrient sensors for glucose. And now what you've probably all been waiting for, what are the nutrient sensors for fat? And now I'm not just speaking of ingested fat, I'm also speaking about body fat. In last episode, we dove very in-depth into leptin. And this is actually going to regulate the increases in body fat. What I mean is that when we increase our body fat levels, we'll increase the levels of circulating leptin. And this in turn will actually work to try and decrease our appetite and increase our metabolism. And really the only thing that can increase the production of leptin is accumulation of body fat, or overeating specifically on the nutrient fat. And conversely, there's a peptide called Neuropeptide Y that I want to focus on. And this is really going to actually regulate when we begin to fall below our normal body fat levels, or we simply are just not ingesting enough fat, we'll begin to upregulate the production of Neuropeptide Y, and this will increase our appetite and decrease our metabolism. And I won't go extremely into depth like last episode about how the leptin system can become dysregulated, but I really think to get a brief rundown on that, going back to last episode would be a fantastic benefit. But the long story short of it is that, very similar to the way that I spoke about insulin resistance, we can develop leptin resistance, where we produce a lot of leptin because we have a lot of fat. But in a sense, we overstimulate the receptors, and the receptors do not begin to respond to this leptin as much. Which unfortunately means that despite having high levels of body fat, our brain isn't actually getting the signal that is being sent from our fat cells. So the brain is kind of thinking that we have low body fat, and therefore it will increase our appetite and decrease our metabolism. And in the same way that having insulin insensitivity causes us to produce glucagon despite having enough glucose, leptin insensitivity causes us to increase food intake despite having enough body fat already. And I will mention that this can technically occur in the reverse. There are scenarios where people can actually become resistant to neuropeptide Y if they go from being extremely overweight and maybe begin to do something like fasting. Because in a fasted state, we will increase production of neuropeptide Y. And the only people that can really prolong the production of neuropeptide Y long enough to actually cause some sort of desensitization would be someone that is very overweight and decides to go on a fast that is over a week, which could be one of the reasons among a myriad of reasons why some people's appetite actually begins to decrease after prolonged fasting. But once again, this would only be able to occur after very prolonged fasting, and most people shouldn't try this because they simply do not have enough body fat to maintain it, which is a good thing. So in terms of fat, our nutrient sensors are going to be leptin and neuropeptide Y. Leptin will tell our brain that we have enough fat, and neuropeptide Y will tell our brain that we do not. So just like the other proteins and hormones, I'm not going to go very in-depth on leptin because this podcast would simply be hours long. However, unlike insulin and glucagon, leptin and neuropeptide Y are actually going to be more mediated through brain circuitry. What I mean is that most of their effects are actually going to be on the brain. And all I really have to say is that this is quite interesting. It seems that the brain really prioritizes understanding how much fat we have, and it keeps fairly tight control of these things. The thing is, we see a lot less dysregulation of leptin and neuropeptide Y than we do of insulin and glucagon. While I won't get into an entire diatribe about this, it really is that fat is prioritized by the body, and the regulation of fat is a lot more important than the regulation of glucose a lot of time. And additionally, it's sometimes a lot more complex. In addition, I don't think I've ever heard of anyone that has dysregulation in their protein sensing system. With that being said, some bodybuilders have talked about becoming anabolic resistant and feel that after too many years of a lot of protein, they don't really get the same effects of protein. But unfortunately, this could actually be the cause of insulin resistance, because insulin resistance actually is one of the key, if not the biggest factor in anabolic resistance as we age. Simply, we don't have proper functioning and signaling of insulin, and we're not taking up as many amino acids, so we simply can't turn on this protein synthesis process to as great of a degree. And this could be occurring in someone like a bodybuilder who is simply living on a very high carbohydrate diet for years on end and begins this insulin resistance cascade. But I'm kind of getting on a tangent. Let's talk about leptin, and maybe we'll come back to this topic at the end of the podcast. So leptin is produced in a circadian pattern throughout the entire day, and will decrease leptin production prior to meals so that we don't have the leptin suppression on appetite. And immediately following a meal, once we begin to sense that there is specifically fat inside of our meal, then leptin production will go up to suppress our feeding. And leptin is produced by the fat cells, and the larger the amount of fat mass we have, the more leptin we produce. So the difference between someone who is lean and someone who is overweight is not the actual pattern of leptin, it is just the amount that they produce. Like I said, leptin is produced in pulses, and they simply release more leptin every time one of these leptin pulses occurs. And in the brain, leptin will actually stimulate what are called POMC neurons. And these neurons are extremely important for the creation of two molecules. One is called alpha melanocyte stimulating hormone, and this will have a myriad of functions that will decrease our appetite and increase our metabolic expenditure. And I talk about this very in depth in episode 42 called Tanning Addiction, the Biology of Tanning, and a whole lot more. As you may have guessed, alpha melanocyte stimulating hormone also plays a role in tanning. But like I said, this hormone will drastically decrease our appetite. But through the process of producing this hormone, we also produce another small molecule. This molecule you may have heard of, it's called beta endorphin, and it's the same thing that is released in response to opioids. And this molecule will increase our feelings of satisfaction and decrease our perception of pain. And I don't know about you, but both of these things simply cause me to reduce my appetite. See, the leptin receptors also increase the production of dopamine, serotonin, and GABA. Serotonin causes us to feel simply satiated with our current state of nutrition. It just decreases our desire to go seek something outside of ourselves. And GABA can inhibit some of the hunger promoting neurons. And dopamine can actually increase both motivation and metabolism by its role in motivation and movement. But because of all the signals that are coming in to decrease the reward value of food, this dopamine motivation can actually be used for things like work or exercise. And it also will inhibit the function of the next peptide we'll talk about called neuropeptide Y. Leptin has an inhibitory effect on this peptide, meaning it will stop the secretion of neuropeptide Y. And you may actually be sensing a theme here. The body has some pretty cool mechanisms to allow proteins or hormones that oppose one another to actually inhibit the functioning of one another. The hormones that respond to high glucose will inhibit the ones that will respond to low glucose. The same is true for protein and fat. And now leptin also has receptors on the fat cells and the muscle cells, and the liver. And it works through the same mechanisms as all the other sensors, in which leptin will either inhibit or increase specific enzymes that will help it do whatever its function is. And it does this through phosphorylation and the activity of these transcription factors. And on fat cells, some of the transcription factors are ones that actually inhibit us from intaking more fat into the cell, but they upregulate the usage of fat through the enzymes that are required for taking fat and turning it into energy. And if you remember, leptin is produced because there's a lot of stored fat. So what the cell is trying to do is stop further accumulation and basically burn off what it has. And another way it does this is actually by turning white fat into brown fat. Now let me explain. They have actually started delineating fat on a spectrum between white and brown. And the more brown a fat cell is, the more mitochondria it has, and the more of a specific protein it has in its mitochondria called uncoupling protein 1. And simply what this protein does is it wastes energy in the form of heat. It simply, instead of making ATP, will release energy in the form of heat that we don't actually use for any sort of process. In a sense, it is wasting energy, but this will actually increase our metabolism, and because leptin is responding to higher body fats, meaning that the more body fat we have, the more leptin we will produce. The more leptin we have, the more uncoupling protein 1 will have, and the more fat will be kind of wasting as energy because we kind of have enough to spare. And NPY, as you may guess, will actually decrease this process. And on the muscle cell, it will actually increase uptake of glucose, but it will also increase the oxidation of fat. And it has some very minor roles of increasing protein synthesis through stimulation of mTOR. Simply, the muscle, once again, is one of the last tissues that will uptake energy. And it's also one of the last tissues that will actually grow in size. But leptin is sending the signal that there really is enough energy available. So it will upregulate some of the proteins responsible for uptaking energy from the bloodstream and actually using this energy for structural reasons. because when we are increasing the utilization of fat, we will actually turn that glucose into glycogen for storage. Alright, the last tissue I want to talk about is the liver, where leptin actually seems to have roles in reducing what's called fatty liver, or the accumulation of fat inside of the liver. The proteins it upregulates in the liver will actually work to break down the stored fat in the liver and release it into the bloodstream. And it also works to inhibit the enzymes responsible for creating more fat, because it would be kind of counterintuitive to increase the enzymes for breaking it down and building it up. Leptin also aids in insulin sensitivity at the liver. So when leptin increases insulin sensitivity, we can simply uptake and store more glucose. And finally, leptin will cause the thyroid to produce more thyroid hormone, which once again works to increase our appetite. So as you can see, all of these mechanisms work to actually decrease the amount of fat that we have and decrease the amount of food that we're eating to decrease further fat storage. And it does this by increasing metabolism and just decreasing our appetite. And if we look at neuropeptide Y, it's the exact opposite. And now neuropeptide Y seems to work in tandem with another peptide called agouti-related peptide, or just AGRP. But in order to have one for each category, I just chose to talk about neuropeptide Y. But once again, this illustrates that none of this is actually occurring in isolation, and there is a multitude of other chemicals and molecules inside of our body that also are playing a role at the exact same time, and they can even mediate the effects of some of these molecules. For example, just because you have higher levels of body fat doesn't mean you're constantly going to be hungry. And the process of actually doing things to reduce your body fat, like putting yourself in a caloric deficit, fasting, or exercise, will actually work to reduce production of leptin and help aid in leptin sensitivity. However, most of these will actually work through increasing production of this NPY, or neuropeptide Y. Simply, you can think of this neuropeptide Y as inhibiting all of the things that leptin does. So on those POMC neurons that are producing the alpha melanocyte stimulating hormone and the beta endorphin, neuropeptide Y is simply just going to inhibit them from producing these molecules. It actually has an interesting effect on corticotropin releasing hormone and oxytocin neurons. It will decrease the production of both oxytocin and corticotropin releasing factor neurons. And both of these molecules are actually able to suppress our appetite. And when neuropeptide Y inhibits the inhibitors, we don't have this brake on our appetite. With that analogy, it's kind of like taking your foot off the brake. If the speed of the car was how hungry you were, when neuropeptide Y inhibits all of these appetite-suppressing hormones and peptides and other molecules, it's simply like releasing your foot off the brake so the speed of the car begins to increase. And the other big effect is that it will reduce the production of thyroid hormone, and it will have a counter-regulatory effect on the browning of body fat. So it will stop this process from actually occurring. And now most of the effects of this molecule certainly are in the brain, but there are receptors on the muscle, fat, and liver cells. And on the muscle cells, it will actually increase the translocation of these GLUT4 receptors. But this will actually increase the glucose uptake and usage at the muscle, because it doesn't appear to have any effects on the glycogen enzymes, but it does on the enzymes that are responsible for turning glucose into ATP. And in this way, we'll actually increase the utilization of glucose and decrease the utilization of fat. With that being said, I think I actually forgot to mention why we produce NPY, or neuropeptide Y, in the first place. So one of the functions of leptin is to actually inhibit the transcription factor for neuropeptide Y. And simply when leptin levels begin to go down, we have less of this neuropeptide Y inhibition, meaning we'll produce more neuropeptide Y. And the times that leptin is going to reduce is when there is insufficient fat. And it also reduces before a meal, which releases the inhibition on neuropeptide Y and increases the production of this peptide. Another thing that stimulates it is actually ghrelin, which is produced inside of the stomach when the stomach is empty. And an empty stomach means no food. However, there are some really interesting things about neuropeptide Y. It seems to be extremely sensitive to fat. What I mean is that a high sugar diet can actually increase the production of neuropeptide Y throughout the entire day. And it is kind of intuitive. It is simply trying to make us use more glucose and less fat because we don't have much fat coming in. And I think it's really interesting that this neuropeptide Y peptide is very responsive to dietary fat. So it seems that mice that are deficient in neuropeptide Y can simply overeat on a high carbohydrate diet until the cows come home. They can simply just continue to eat carbohydrates and not really feel full whatsoever. However, when their diet is changed to a high fat diet, they simply do not gain as much weight, which demonstrates that there is some sort of production of leptin because of the high fat diet, which allows them to actually begin to mitigate their hunger. And now on the fat cell, it simply just reduces the production of a lot of the enzymes that are responsible for breaking down triglycerides or stored fat, but it will increase the production of enzymes required for taking fat from the bloodstream and storing them into fat cells. And it really does the exact same thing inside of the liver. And it also promotes the expression of what are called gluconeogenic enzymes, or just the enzymes that will produce more glucose through gluconeogenic substrate, which again are glycerol, amino acids, and lactate. One of the interesting things is that this neuropeptide Y really seems to kind of negatively impact the insulin receptor. So in the way that leptin phosphorylates a specific protein that increases the function of the insulin receptor, neuropeptide Y will actually inhibit this protein. So we have a decreased insulin sensitivity. And the only real explanation for this I could come up with was that the body is trying to actually spare the glucose for the muscle, so the muscle will begin to use less fat, or simply just reduce the uptake and storage of glucose at the liver. Therefore, other tissues can use more glucose and use less fat, once again sparing fat, because that really is the role of this neuropeptide Y peptide. So really what neuropeptide Y does is it shifts our metabolism away from using fat as much as possible and towards using other things, predominantly glucose and amino acids for gluconeogenesis, and glycerol and lactate. And it will also increase our hunger by basically suppressing all of the appetite suppressing peptides. So really inhibiting the inhibitors. And then decreasing our metabolism by once again just inhibiting all of the molecules that will work to increase our metabolism, specifically leptin, which has the effect of increasing thyroid. And downstream actually has the browning effect, which neuropeptide Y will inhibit. So I think these 6 molecules are really a great demonstration of how the body has pretty tight control over the nutrients it has in storage, the nutrients it has coming in, and the status of the body in general. And I kind of want to come back to the topic of the body seems to be really good at regulating amino acid availability and fat availability. But the body doesn't really regulate the carbohydrate influx as readily and as well, which is why we often see so many diseases where we have very altered blood glucose simply because the regulation of these two hormones, insulin and glucagon. And now the best explanation really would be that we simply just do not have as much genetic information about really how to keep these hormones and their balance, including the receptor, in check. But in terms of mTOR and AMPK, there really is no dysregulation in this system. And in terms of leptin and neuropeptide Y, really the only way that this system becomes dysregulated is when we drastically overconsume. And unfortunately, it would be extremely difficult to overconsume just on fat and protein. So the overconsumption typically comes in the presence of a lot of carbohydrate, which the accumulation of fat will cause the dysregulation in the fat sensing system of leptin resistance. But once again, it may actually be caused by the carbohydrates. And this definitely isn't me saying that carbohydrates are the devil or they're evil in any way. However, we've been eating fat and protein for far longer than we've been eating sufficient carbohydrate. So the body is highly specialized to do very well on a diet mostly comprised of fat and protein. Looking back at the research, the reason that the human brain actually expanded was because we began eating animals. Simply the transition away from actually eating all those carbohydrates to beginning to get most, if not all, of our nutrition from animals, which, as you may or may not know, only contain fat and protein, is actually what allowed our gut to shrink and our brain to expand. And I hope to do an entire podcast on this, but this is called the expensive tissue hypothesis. We used to have very large stomachs, think of something like a gorilla, and these gorillas eat a lot of carbohydrates and need a very long and complex digestive system to break it all down and actually supply themselves with energy. But because this process is so energy intensive and because this tissue is so, for lack of a better word, expensive, they have much smaller brains than humans. And when we began eating meat, we actually were able to decrease the size and the energy demands of our stomach, allowing us to increase the size and energy demands of our brain and allow for higher cognitive functioning. And this really is when we adapted into the humans we are today, so it makes sense that a lot of our genetics are kind of set up for a diet that is very rich in animal foods. Once again, meaning that it's going to be rich in fat and protein and not abundant in carbohydrate. But we definitely have been eating carbohydrates for a fairly long period of time, and we are making a lot of adaptations to carbohydrates. However, there's really no way to make adaptations to some of the foods that we have today that are extremely processed and extremely rich in both carbohydrates and fat, and not really that rich in protein. So we end up overeating and really messing with these nutrient sensing pathways. The body gets kind of confused when there's a lot of carbohydrates and a lot of fat, but not much protein. As I mentioned, a lot of carbohydrates that stimulate insulin also stimulate this mTOR. And actually, one of the problems with this is if we stimulate mTOR without taking in exogenous amino acids, we may actually begin to degrade some of the healthy amino acids in other tissues and other cells in order to supply the cells that have an activated mTOR with the amino acid. What I mean is that if we have increased blood flow to maybe our legs, we'll have greater insulin activation inside of our legs and less insulin activation in our upper body, meaning that more of the cells inside of our lower body will be stimulated by insulin, therefore more of the cells in our lower body will have an activated mTOR. So we may promote protein synthesis in these cells simply by traveling up to our upper body where we don't have an activated mTOR, but we have an activated AMPK, and start pulling some of these amino acids so we can use them in our legs. With that being said, this is probably a topic for a whole new podcast, so I'm going to leave this one here. I really hope you enjoy, and I hope you learned a few things. And if you think I missed anything or have any further questions, feel free to reach out in all the platforms in the description, or just reach out to me on Instagram at Calvin_Scheller. Thank you for listening and have a great day.